In 1967, a 24-year-old graduate student found something on her chart recorder that shouldn't exist and almost threw it away. Jocelyn Bell was scanning radio telescope data at Cambridge night after night looking for quasars. The work was tedious, methodical, unglamorous. But on August 6, 1967, she noticed a signal that didn't match anything in the astronomical catalog. A pulse, regular, impossibly regular, coming from deep space, repeating every 1-3 seconds with the precision of an atomic clock. She had no idea what she'd found. Her supervisor, Antony Hewish, was skeptical at first. The signal was so perfectly timed, so mathematically clean that the team half-jokingly called it LGM1, little green men. They genuinely wondered if they'd detected an alien transmission. Remember, they didn't know yet what they were looking at. None of them did. Within weeks, they found another one, then another, 4 pulsars in total, each with its own rhythm. The alien hypothesis evaporated. Something else was happening at the edge of human understanding. The team published their findings in February 1968. Jocelyn Bell's name appeared second on the paper. Hewish would later win the Nobel Prize. She would not. But here's what matters, what those pulsars actually were. Within months, theorists understood. A pulsar is the crushed heart of a dead star. When a massive star explodes, goes supernova, its core collapses. Protons and electrons are forced together, becoming neutrons. The entire mass of our sun gets compressed into something the size of a city, a neutron star. A teaspoon of neutron star material would weigh as much as Mount Everest. Gravity is so extreme that it flattens atoms completely. But there's more. These dead stars spin. Some rotate dozens of times per second. And as they spin, they beam radiation like a lighthouse out into space. We see a pulse every time that beam sweeps past Earth. The precision is what changes everything. The best atomic clocks on Earth, the ones that keep GPS running, that synchronize global financial networks, those clocks drift. Over months, they lose nanoseconds. Pulsars don't. Some pulsars are more accurate than any human-made instrument we've ever built. We're talking precision to within milliseconds over millions of years. By the 1970s, astronomers realized something remarkable. They could use pulsars like cosmic metronomes. If you measure the arrival time of pulses from a distant pulsar, tiny variations tell a story. A pulsar signal slows fractionally if gravity is bending it. It arrives earlier if something massive is pulling it. Pulsars became our eyes for seeing the invisible. In 1974, 2 astronomers named Russell Hulse and Joseph Taylor discovered a pulsar orbiting another neutron star, a binary pulsar. They watched it for years, tracking its orbit with millisecond precision. And they found something extraordinary. The orbit was shrinking, slowly but measurably. The 2 stars were spiraling toward each other. Why? Einstein had predicted it decades earlier. Massive objects moving through space don't just bend gravity, they create waves in the fabric of spacetime itself. Gravitational waves. The orbiting pulsars were losing energy by radiating those waves. They were giving off ripples in reality, and we were measuring it indirectly through a pulsar's clock. Hulse and Taylor won the Nobel Prize in 1993. The pulsar had given us proof that gravitational waves were real, but we still hadn't directly detected one. We'd only seen their fingerprints in a pulsar's rhythm. That would take another 23 years and an entirely different kind of instrument. In September 2015, the Laser Interferometer Gravitational Wave Observatory LIGO detected something. A signal. 2 black holes a billion light-years away had collided and merged. The gravity wave from that collision had rippled across the universe and passed through Earth. LIGO caught it. Millisecond precision. The same kind of precision pulsars had been teaching us to measure for 40 years. But pulsars aren't finished teaching us. Astronomers now use arrays of pulsars, dozens scattered across the sky, to hunt for even larger gravitational waves. Waves from supermassive black holes orbiting each other at the hearts of galaxies. Waves from the universe itself vibrating in its infancy. Pulsars are the tools that will help us see it. A lighthouse in the cosmic dark. That's what a pulsar is. A beacon from a dead star rotating in the void, keeping time with a perfection that makes our finest clocks look clumsy. And because it keeps time so perfectly, we can measure the universe in ways that were impossible before. We can see gravity itself. Jocelyn Bell Burnell, now in her 80s, has received countless honors since that August night in 1967. She's been called the woman who should have won the Nobel, but she's also spent her career advocating for equity in science, for the recognition of contributions that were overlooked. Her pulsar discovery was the beginning. It was also a lesson about who gets to tell the story of discovery. Today, pulsars are more than historical footnotes, they're active instruments. NASA Fermi Telescope tracks gamma-ray pulsars. The Event Horizon Telescope uses pulsar signals as calibration points. And the next generation of radio observatories, the Square Kilometer Array, will find thousands more, each one a clock, each one a tool. We live in a universe that reveals itself through precision, through small signals patiently measured, through the persistence of people willing to stare at chart paper for hours looking for something that shouldn't be there. A pulsar is a reminder that the most profound discoveries sometimes look like noise until someone decides to pay attention. Subscribe so you don't miss the next untold story from the frontiers of space, where the most precise measurements reveal the deepest truths.